exercise of unit current electricity. First question. Storage battery of EMF 12 volt, internal resistance 0.4 ohm. What is the maximum current? Okay, the quantities are given. Equation for maximum current I is equal to epsilon divided by R. So you will get the value of maximum current. Then come to question 2. A battery of EMF 10 volts, internal resistance small r is equal to 3 ohm. Then current I is equal to 0.5 ampere, R is equal to 3 ohm. What is the terminal voltage and what is the resistor R? So you can use the formula I is equal to epsilon divided by R plus R. From this formula you can find the value of R. Once you get the value of R, you can calculate the terminal voltage using the formula V is equal to IR. V is equal to I. Then next question 3. 3 resistors 1, 2 and 3 are series. And what is the total resistance of the combination? Then total resistance is 6 ohm series combination. And if the combination is connected to a battery of 12 volt and negligible internal resistance, so obtain the potential drop across each resistor. So you can calculate current in the circuit. I is equal to V by R total. 12 volt battery is used. So V you can take a 12 volt or V. We can say it is epsilon divided by capital R. Epsilon is given 12 volt. So you will get the value of I. Then V1 you can calculate as I into R1. Then the same way V2 is equal to IR2 and V3 is equal to IR3. Then next question 4. 3 resistors are connected parallel. What is the total resistance? Parallel resistance formula you have to use 1 by RP is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Now in parallel combination, voltage remains same. So across each resistor, constant voltage is there. So currently you can calculate using the formula I is equal to epsilon divided by R1. That is the value of I1 for first resistance. And second resistance I2 is equal to epsilon divided by R2. And the same way you can calculate the value of I3 also. I3 is equal to epsilon divided by R3. So you will get all three values. And total current will be the sum of I1, I2 and I3. The total current drawn from the battery. Then next at room temperature 27 degrees Celsius it is given. Resistance is of heating element is 100 ohm. What is the temperature of the element if the resistance is found to be 117 ohm? Value of alpha is also given. So there you can take you can use the formula R is RT is equal to RT. We have to take as 170. 170 must be taken as RT. RT is equal to R naught. R naught can be taken as 100 ohm into 1 plus alpha T minus T naught. T naught will be 27 degrees Celsius and T we need to find out. And in that question, first find the value of T minus T naught. Rearrange the formula and find the value of T minus T naught. Once you get the value of T minus T naught, substitute the value of T naught there and find the value of T. Then, question 6. A negligibly small current is passed through a wire of length 15 meter. Length is given, L is equal to 15 meter. Then, uniform area cross section. Area cross section A is given. Then, the resistance is measured 5 ohm. R is equal to 5 ohm. What is the resistivity of the wire at that temperature? Resistivity formula rho is equal to Ra by L. Ra by L. All quantities are given. You can substitute the values and find the answer. Question 7. A silver wire has a resistance of 2.1 ohm resistor ohm at 27.5 degrees Celsius and resistance of 2.7 at 100 degrees Celsius. Determine the temperature coefficient of resistivity. Okay, here first you have to find the value of R naught and temperature is T1 is given and T2 is given. R1 and R2 are also given. The temperature coefficient of resistivity you need to find alpha is equal to, the formula is RT minus R naught divided by R naught into T minus T naught. R naught into T minus T naught. All quantities are given there so that you can find the value of alpha. Then question 8. Heating element using nichrome connected to 230 volt. Voltage is given. Then initial current I1 is equal to 3.2 ampere, which settles after a few seconds to a steady value 2.8 ampere, which you can take as IT. You know, when current passes through the conductor, heat will be produced, temperature increases. When the temperature increases, for an ordinary conductor, temperature increases, its resistivity increases. So resistivity increases, naturally current decreases. And what is the steady temperature of the heating element? If the room temperature is 27 degree Celsius, which you can take as T naught. T naught is equal to 27 degree Celsius. Then alpha is also given 1.7 into 10 power minus 4 per degree Celsius. So first what you have to do, you have to find the value of R naught and RT. So R naught is equal to V divided by I. and RT is equal to value you have to find out. RT is equal to V divided by I2. So you will get the value of RT. Now you have to calculate the steady temperature. So as I mentioned in the previous problem, first find the value of T minus T naught. T minus T naught is equal to RT minus R naught divided by R naught alpha. So substitute the values, find T minus T naught. Once you get to T minus T naught, you find the value of T naught and find the substitute the value of T naught and find the value of T. Then next question 9. When you solve the questions like this, the first part you have to check this question whether the conditions of Wheaton bridge is satisfied or not. Here you can see the situation ratio you have to take. You know, Wheaton bridge means it is up and down ratio or left to right ratio. So up and down ratio, if you take a 10 by 5 and a 5 by 10, or it is left to right ratio when you take 10 by 5, 5 by 10, means the ratio is not satisfied. If ratio is not satisfied, then you can conclude it is not a balanced Wheaton bridge. As it is not a balanced Wheaton bridge, there is no other option in front of us. We have to go for Kirchhoff's rules. That's all. So now we have to take the loops. So first I am going to take the loop A, close to loop A, B. This point non-name is given, so take it as D. A, B, D, A. First A, B, D, A. Values of current we need to take. So first this current I am going to mark as I1. Here current I2. So that the current in this branch is I1 plus I2. Current here is I1 plus I2. Then current here, the middle branch, we take I3. So that current here in this branch along BC, it becomes I1 minus I3. So current here in BC becomes I2 plus I3. I2 plus I3. And finally, these two currents are added so that here again current becomes I1 plus I2. I1 plus I2. And for convenience, we can give a name here. This point E and this corner here. So that much we have to label in the diagram. Then take a closed loop ABDA. Apply Kirchhoff's rule with the sign convention, proper sign convention. You will get 10 I1 minus 5 I3 plus 5 I2. There is no cell there, so take it. EMF will be equal to 0. You can simplify the equation. You will get 2 I1 minus I3 plus I2 equal to 0. So take it as equation 1. Next, take the loop BDCB. Take the loop BD. Sorry, BC loop B, C, D, B. Then write the loop equation. So here minus 5 into I1 minus I3 because current is in clockwise direction in that resistance, plus 5I3. In that loop you can see current is anti-clockwise direction, plus 10 into I2 plus I3 because in branch DC current is in anti-clockwise direction. So here also there is no cell, no EMF, so you can take it as 0. Therefore you will get minus I1 plus 4I3 minus I1 plus 4I3 plus 2I2. 2I2 equal to 0. Equal to 0. So take it as equation 2. Now next we have three unknowns are there, so we need three equations. So take the loop A, D, C, E, F, A. Then write the equations. So here cell sends the current in clockwise direction. Cell sends the current in clockwise direction. So that also we need to consider. Here you will get a minus 10 into I1 plus I2 minus 10 into I1 plus I2 minus 5I2 minus 10 into I2 plus I3 is equal to minus 10. Equal to minus 10. Then simplify the equation. You will get minus 2I1 plus 5I2 plus 2I3 plus 2I3 equal to 2. So take it as equation 3. So now you got three equations. It is up to you how to solve these equations. Okay. So you have to take equation 1, 2, and 3 and solve. That's all. Okay. So one of the methods you can follow like this. You can take equation 1 with equation 1. Uh, you can multiply equation 2 by minus 2. Equation 2 into minus 2, then add it with the equation 1. Then you will get I2 is equal to minus 3I3. I2 is equal to minus 3I3. Take it as equation 4. Then substitute equation 4. Substitute 4 in equation 3. Substitute 4 in equation 3. you will get I1 is equal to 1 plus 13 by 2 I3. So take it as equation 5. Then substitute 4 and 5. Okay, substitute 4 and 5 in equation 2. Substitute 4 and 5 in equation 2. Then you will get the value of I3. You will get value of I3. Then again you can use equations 4 and 5 so that you will get the values of I1 and I2. Values of I1 and I2. Once you get the values of I1, I2 and I3, you can find the current in each branch. So that's the method you have to follow. Then next question, in meter bridge, the balance point is found to be 39.5 centimeter. You can take it as L1 from NDA. When the resistor Y of 12.5 ohm means the resistor in the other gap, determine the resistance X. Here one figure is mentioned, that's not very clear. So you directly use the formula X is equal to RL divided by 100 minus L. Meter bridge formula you can use. RL divided by 100 minus L. L is given 39.5. Okay. Now, next, why are the connections between resistors in a Wheatstone or a meter bridge made up of thick copper strips? Thick copper strip means you have to take its area is high. When area is high, resistance, when area increases, resistance decreases. So resistance decreases means if you use a wire, thin wire, its area cross section is less, it has more resistance. Actually, we are observing the balancing of resistance there. So the resistance of the connections will not affect our reading because we are connecting particular resistance R1, R2 and all. So the resistance of the connections should not affect our resistance measurement. That is why we use a thick copper strip having large area and less resistance. Then determine the balance point if X and Y are interchanged. If X and Y are interchanged, then what will happen? Now, if you take the meter bridge, okay, meter bridge diagram should be in your mind. So here we can have the meter bridge wire, 100 centimeter long. Here we have resistance X, just assume like that. Here you have resistance Y. And what happens here? The balancing length we can take. This is L and this part is 100 minus L. So you can take like this, the resistance X is balanced by a length L and resistance Y is balanced by a length 100 minus L. Now X and Y are interchanged. When X and Y are interchanged, what will happen? Then the same situation you can take when X and Y are interchanged. Okay, here you will have Y, here X. So 100 centimeter wire. So now the Y is balanced. This part is balanced by a length 100 minus L, and this will be L. So what happened? Ultimately, what happened? If L was 40, okay, always we are measuring the valence point from a particular end, suppose NDA. So when X and Y are in the first arrangement, suppose L is equal to 40 centimeter, then 100 minus L is 60 centimeter. Now when interchanged, what happens? The first part will be 60, second part will be 40. So this is the balance point now. That means actually what happens to the balance point? If it was L in the first arrangement, it becomes 100 minus L in the second arrangement after interchanged. Okay, so what is your answer? The answer, the valence length becomes 100 minus L. That is the answer. Now part C, what happens if the galvanometer and cell are interchanged at the balance point of the bridge? Would the galvanometer show any current? So if it is interchanged, no change will be there. You can see the Wheatstone bridge circuit like this. Okay, so if you are connected like this or a galvanometer, okay, so just like I will draw a diagram here. Suppose Wheatstone bridge, in this way resistance, sorry, no resistance. You can connect the galvanometer here and battery here like this, or the same arrangement we can do in this way. Connect galvanometer here and battery here. So in both cases you can see it is just like a bridge. It's all just orientation changes, that's it. Therefore no change is the answer. The bridge is balanced, again what will happen? It will remain balanced. You cannot obtain any change there. Again the bridge will remain balanced so that no current will pass through galvanometer. Just the orientation changes, that's it. Now come to question 11. Storage battery EMF 8 volt and a charging cell of 120 volt. Internal resistance of the battery is 0.5 ohm. Resistance of the resistor R is equal to, means a series resistor is connected. So first one you have to understand the circuit. So here there is a cell. Its EMF is given 120 volt, that is a charging battery. Then a series resistor is connected. Series resistor R value is given there. Then another cell is there here, a secondary cell which we need to charge. And this cell has a small internal resistance also there, which we can represent like this. Internal resistance value is given there, 0.5. Okay, so like this you can connect for the purpose of charging. Then when you charge, what will happen? The positive of the charging battery you have to connect to the positive of the cell. So what is the reason? So usually if you observe, you can see what direction current goes in this cell. Now the charging battery has more EMF, so current will flow in the direction of its EMF. Now take this 8 volt battery. In an ordinary condition of discharge, what happens? Current will come out from the positive terminal. Okay, so like this, current will come out from the positive terminal for 8 volt battery at the time of discharge. Now this is a case of charging, so current should flow in the opposite direction like this, because we want to reverse all the reactions inside the cell. Whatever chemical reactions you obtained when the cell discharges, now you need to get opposite reactions during charging. So current also should enter there in the opposite direction. So that is the situation, that part. That is the reason positive of the charging battery, we need to connect with the positive of the secondary cell there. Then after connecting in that way, we can see the situation there. First of all, we have to take, in this arrangement, we have to take the total EMF. You can see cells are connected in opposite order. Therefore, the effective EMF will be epsilon is equal to epsilon 1 minus epsilon 2. You have to take, that is 120 minus 8. You will get a 112 volt. That is the effective EMF. Now, find current in the circuit. Current I is equal to epsilon divided by R plus R. Effective EMF you have to take epsilon divided by R plus R. So you will get I is around 7 ampere. Now calculate what is the voltage drop across resistor capital R. You can use the formula V is equal to IR. Substitute the value of I and capital R. You will get the answer around 108.5 volt. So total 120 volt is given here. From this 120 volt is dropped across capital R and small r in the secondary cell. This is small r in the secondary cell. So it is just like a series combination of resistors, capital R and small r. So total 120 volt, and this 120 volt, how much is dropped across external resistor capital R? 108.5 volt is dropped across external resistance capital R. Remaining voltage is dropped across the terminals of this 8 volt battery. So how much is the remaining voltage? The terminal voltage of the 8 volt battery. Okay, terminal voltage of 8 volt battery. Terminal voltage, I am going to write VT here, is total applied voltage 120 minus the voltage lost across capital R, that is 108.5. Therefore, terminal voltage is equal to 11.5 volt. Here the difference in situation you have to understand. Usually, according to our formula, V is equal to epsilon minus IR. Epsilon minus IR. EMF is greater than terminal voltage. But in this question, you are getting terminal voltage is greater than EMF. So why terminal voltage is greater than EMF during charging? So charging you have to take as a separate situation. During charging, terminal voltage is greater than EMF. Why? I told in this case, when discharge occurs, current goes from positive terminal to negative terminal during discharge. But during charging, current enters in the positive terminal. That means current changes its direction. As the current changes its direction, we cannot use this formula. We cannot use this formula because current is in the opposite direction. So if current is in the opposite direction, then which formula you have to use? Instead of this formula, you have to use the formula V is equal to epsilon plus IR. V is equal to epsilon because current is in the opposite direction. And if you use this formula, then also you will get the answer 11.5 volt. Okay. So understand the situation. This is the cell equation during the charging of a cell. Then second part of the question, what is the purpose of having a series resistor in the circuit? Why should we connect a series resistor capital R in the circuit? The purpose of connecting series resistor capital R, actually suppose capital R is not there, then what will happen? If in the absence of capital R, if capital R is 0, then current becomes epsilon by small r, and epsilon is 120 small r is 0.5. So it becomes around 240 ampere current. In the presence of external resistance capital R, current is 7 ampere only. We calculated here. In the absence of capital R, current becomes 240 ampere. This 240 ampere current is very high current that will damage all circuit wirings, everything. So what is the purpose of using capital R there? The capital R series resistor capital R is used to reduce the current in the circuit. It is used to reduce the current in the circuit. Okay, so this question you have to note separately. Now, next, move to question 12. In a potentiometer arrangement, a cell of EMF 125 volt, sorry, 1.25 volt gives a valence point 35 centimeter. If the cell is replaced by another cell, the valence point 63 centimeter, what is the EMF of the secondary cell? So it's only a direct calculation. You have epsilon 1 divided by epsilon 2 is equal to L1 divided by L2. L1 and L2 are given. Epsilon 1 is also given. Cross multiply the equation and find the value of epsilon 2. Then next question 13. The number density of free electrons in a copper conductor is 8.5 into 10 power 28 per meter cube. Number density means it is n, number of electrons per unit volume. Length of the wire is given, area is given, current is given. Now you are asked to find how long does an electron take to drift from one end to the other end, which means you need to calculate the time taken by the electron. How to calculate the time taken by the electron? So take the formula I is equal to NEAVD. Cross multiply the equation. VD is equal to I divided by NEA. Once you get the value of VD, you can calculate time T is equal to distance traveled divided by speed. Okay, substitute the value of VD in this equation and find the value of. So in that way, the time taken by the electron to travel the length of the conductor can be calculated. Now, question 14. See the data given, sigma, the surface charge density is given, current is given, radius of earth, okay, radius of earth, these all factors were given. Now, what you are asked in the question, how much time would be required to neutralize the charge coming towards earth surface? That is what given there. So there, first you can calculate area of the earth surface. A is equal to 4 pi r square. Then once you get the area, you can calculate the charge reaching over there. Q is equal to sigma A. Then time you can calculate, time T is equal to charge divided by current. Current is given. So T is equal to Q by I will give you the answer. Now, question 15. Two lead acid, 6 lead acid type secondary cells. Secondary cells means the cells that can be recharged. So you can, a secondary cell you can recharge. Okay, then each of EMF 2 volt. Therefore, we can say the total EMF will be 6 volt. So 6 into 2 volt. So it will be 12 volt total EMF. Then internal resistance 0.015 ohm are joined in series to provide a supply to a resistance of 8.5 ohm. 8.5 is the external resistance, 8.5 ohm. External resistance 8.5 ohm. Internal resistance is there. Internal resistance of each cell is given. So into 6 will give a total internal resistance. Then what is the current in the circuit and terminal voltage? Again, can use the formula I is equal to epsilon divided by R plus, I'm going to write here 6R. So you will get the value of current. Once you get the value of current, then you can again use the formula V is equal to IR to find the terminal voltage. V is equal to IR. Then a secondary cell after long use was an EMF of 1.9 volt and large internal resistance 380 ohm. What is the maximum current that can be drawn from the cell? Okay, again can use the formula I is equal to epsilon divided by small r is the equation for maximum current. Then could the cell drive the starting motor of a car? So there you have to see. When you take the case of the car, okay, a car battery is a bulky acid battery, and its voltage will be 6 volt, 9 volt, like that. Then such a small dry cells are also available in the market. Then why can't we use a small dry cell of 9 volt to start the car? What is the reason we need to use a bulky car battery, acid batteries and all? Okay, the reason is that acid batteries are having very less internal resistance. Small r will be very small. So we need more than 100 ampere current to start a car. That initially we need a very high current. So this small tri-cell of 9 volt having high internal resistance, capital R is high. Therefore, it can give only very less amount of current in terms of milliampere and all. But if the car battery of same voltage, you can see its internal resistance is very, very small. Therefore, it can give very high current. Okay, so car needs very high current to start its motor. Therefore, we need to use a cell having very low internal resistance. So we obtain high current. In this case, you cannot use this cell because you see its internal resistance is very high and the value of current you are getting is extremely small. So you cannot use that secondary cell to start the motor of a car.